Hello everyone, so my name's Pringle, I'm a data scientist at FinAI, and today I'm going to be talking about how we use MXNet for the task of intent classification. Let's see, let's do it full screen. Which is a kind of text classification model. So FinAI builds digital assistants for the banking sector. So we sell a service to banks that allows essentially their end customers to interact with their bank account conversationally. So you can imagine moving money around, maybe checking interest rates, or maybe topping up your credit card, for example. And my focus at FinAI is really building out the deep learning models that drive our in-house natural language processing software. So like I said, today I'm going to talk about intent classification, and this is a text classification problem. So text classification, for those of you who aren't aware, is a supervised learning problem where we're simply taking some input text and mapping some output label. So you can see here that we're taking documents and classifying those as either technology, sports, or entertainment. And typically this can be done at either the document level, as you see here, or either at the paragraph or even the sentence level. And I think one of the things to focus on here is that this involves a lot of manual human annotation in some cases. And so those categories are actually defined by humans and labeled. And so the setup is, for example, I could take 10,000 movie reviews and annotate those as either positive, negative, or neutral sentiment, and then train a model to do the same that I've done, and then deploy that in production and use it on new text data to predict some categories. So the setup is that we're training the model to mimic the annotator. So any task where you can imagine yourself consistently annotating to some category, the chances are that it's possible to do that with a machine learning model as well. And so, for example, detecting whether an email is spam or not, maybe you're detecting abusive comments in online forums, maybe you're trying to track customer sentiment over time, or let's say, for example, you receive 5,000 customer feedback messages every day, and maybe you want to identify which of those are insightful feedback. If you can imagine consistently annotating customer feedback as either insightful or not, then that may be a good candidate for a text classification model. But I think one thing to focus on is that the techniques used for text classification will just allow you to ingest text into other kinds of models as well. So say, for example, you're building a recommend system to model the interaction between users and items. There's every chance that your users or items will have text features. And so some of the things I go over today may be useful for other kinds of models that you're building. So intent classification is essentially text classification in the context of natural language processing. So this is how we use text classification at FinAI. So you can see here that the user asks the balance of their checking account, and there's two machine learning models here. So the first machine learning model is an intent recognition model, and this is just classifying that input text to one of maybe 50 or 100 different categories. So you can see here that we detect that this text corresponds to the get balance intent, we would call it. The second thing that happens is there's a machine learning model called a tagging model or an entity recognition model. And this is looking for named entities in that input text. So here that model extracts that the token's checking account correspond to an account name. And so between the intent and the entities that we extract, we can then try and respond intelligently to the user and execute some business logic. So I'm going to show a quick example of how we're using MXNet today, but before I do that, I just want to talk through a model that we have used in the past for text classification. So the setup here is that we have some utterance come in. So the utterance comes in, I like this movie very much. The first thing that we do is tokenize that utterance, and for each individual token in our training data, we're going to build what's called a lookup table, which will contain some 5-dimensional representation of each word in our vocabulary. So we retrieve the embedding for each of these tokens, and then we're going to have various convolutional filters pass over that input sentence matrix. And so each of these will produce a feature map, as you can see here. And the height of that feature map really depends on the height of the filter that is used here. We're then going to apply some ReLU activation function, for example, to that feature map before using max pooling to map down to a single feature per convolutional filter. And then we'll concatenate all of those features before applying dropout regularization. And then we're going to build a fully connected layer that will map down to the number of output classes in our problem. So here you can see we've got 2 output classes, and that's because this example is actually for sentiment analysis, so positive or negative sentiment. And this output layer will apply some softmax function so that we can interpret our outputs as predicted probabilities over the classes. And then we'll use the cross-entropy loss to train this model. So just to focus on what the learned parameters are here, we're learning that fully connected, the weights in our fully connected layer, and we're also learning the weights in our convolutional filters. And depending on what we choose to do, we can also learn the weights in our lookup table, or we'll learn those embeddings. So, oh no. Okay, anyone get me on Wi-Fi here? So here we're reading a public news set data set. This is the AG News data set. So we've got 120,000 news articles, and each of them has a corresponding title, description, and class. And what we're going to do is build the model that I just described to map from this description to the class over here. So this is a pre-processing class that does 3 things really. So it's going to tokenize our text. We're then going to pad or slice the text in each training example to some fixed length. And then we'll convert each of our tokens to some index mapping. So if I just show you here, so you can see we build this preprocessor class and we're going to fit it to our features and labels. And so here I'm just printing those index mappings. So when you fit the preprocessor to your training set, you essentially build a mapping from each of the labels, so business, science or technology, etc., to some index. And then we're also building a vocabulary, and I'm just showing the first 10 tokens in this vocabulary, but that maps from each token to some index value. And so now we can use this preprocessor to transform our description to our features, X, and transform our class to our labels, Y. I think it's a bit clearer if you just look at, so now we can use this preprocessor here to transform some text that is certainly not in our training or test set. And so you can see here that actually what happens is we transform this utterance, we split it into individual tokens. Any token that is not in the vocabulary that we just built on the training set will be represented with an index of -1 here. And we also pad it to a constant length, so we're padding this to a length of 20 tokens. And you can see that we have 49,700 or so tokens, unique tokens in our training set. So now that we've preprocessed that data, we can build some data iterators. So here I'm just converting those X and Y to NumPy arrays and building MXNet ND array iterators with a batch size of 120. And just so you can see what what each batch of data will look like, this is the first batch in that training iterator. And so we have 120 examples, each 20 tokens long. And we have 120 labels. So this here corresponds to one single text input, and that has the label 1. So this is the data that we're going to feed to our neural network. So here I'm building the model symbol. So this is exactly what I just described on the image earlier, although a slightly larger model. So we have some embedding symbol here, which is going to build our lookup table based on the vocabulary size, and embed each token with some number of embeddings. We then reshape that and pass it through a convolutional ReLU and max pooling operation. And we're going to do that for each of our different sizes of filters. So in that image we had filters of, I think, height 3, 4, and 5. And so for each of those we'll do this operation. Then we concatenate the outputs, reshape them, apply dropout regularization, and then we're going to map down to the number of labels in our problem, in our classification problem, using this fully connected layer, before using this final symbol, which is a combination of applying the softmax function and applying the cross-entropy loss. So here I'm just building that network symbol. We're going to embed each token with dimension 16. Our vocabulary size is decided in the pre-processing step, along with our number of max tokens. And we're going to have 100 filters of size 3, 100 of size 4, and 100 of size 5. And we're going to pretty aggressively regularize this network with dropout of 0.85 here. And so this is actually trained in a notebook on my Mac. And you can see that on this data set, where state-of-the-art is around 92% test score, we're reaching 89% with this model within 3 epochs. So I think this kind of demonstrates the power of a model like that, because we're training on a CPU, we haven't done any hyperparameter optimization, and we've also discarded any of the data in our training records that was beyond 20 tokens. So I just want to show how we might use this model. So this function just takes in the text and preprocesses it and passes it through our module. And so you can see here I'm selecting a random text example from the test set, and you can see just how much data we would be actually discarding here. This has the label science and technology, and the output of our model is the predicted probability across all of the classes. So we have 4 classes here, and typically we would take the highest confidence class as our prediction with this model. So that's really a toy example, and what I want to spend the rest of this talk talking about is how you might get serious about improving this model if you were going to deploy it in production. So the first feature of MXNet that we found incredibly useful is something called bucketing. So what this allows you to do is, for each batch that passes through your model, you can define a different sequence length. And so one of the disadvantages of what I just did in that example there was we discarded data beyond 20 tokens, but we also did a lot of computation on padded data. So any very short messages, we have a lot of padded tokens in there. And so but what bucketing allows you to do is really choose a sequence length per batch, and each of those different sequence lengths will correspond to a different feed-forward network architecture. And you can then share the network parameters between the buckets. So if I were to go back to the image here, you can actually see if I were to double the length of this input text, we would have the same number of weights in our convolutional filters. We would have we'd have longer outputs in our feature maps, but then after the max pooling step, we're still going to have a single output here, and therefore our penultimate layer will be the same size. So the weights in our filters are the same, and actually the weights in our final fully connected layer are the same, which means this is a prime candidate for bucketing. And really the advantage of this for us has been that it's drastically reduced the time it takes to train our models, and it also allows us to respond to very long messages from the user. So we don't have to discard data past a certain sequence length. And we have seen sort of small improvements in our test metric as a result of not discarding that information. I think the second thing that we found really useful is pre-trained embeddings. So in that example, I initialized the lookup table, and we actually drew some parameters from, I think, a uniform distribution. I have to go back and check that, but we learned the embeddings that correspond to all of our tokens. So one other thing you can do is use a pre-trained word embedding library. So I've linked some papers that would be worth reading about that here. But essentially, a pre-trained word embedding is a numerical representation of a word that represents its context. So, for example, the words king and queen will have similar numerical word embeddings because they will appear with similar words around them. So now we can pass some meaningful embeddings into our model before we train them. And you've got two choices here. Either you can fix that embedding, or you can actually decide to fine-tune it through backpropagation. And Glue on NLP is awesome for this because within sort of 3 lines of code, you can read fast text embeddings into your Python script. And particularly, one of the things we like about fast text is it has support for out-of-vocabulary words. So in the example I showed, we have 50,000 unique tokens. And the problem with that is in production, it's quite likely that you're going to encounter new tokens. And so you won't have some learned embedding for those. If you use a pre-trained word embedding library, you can have well over 1 billion tokens to draw from in production. And also if you use something like fast text, even if that token is not in the vocabulary, there's support for still trying to build a meaningful embedding. for those words. Character level features we've seen benefits with as well. So even if you have a massive pre-trained word embedding library, it's still possible to encounter new words in production or new tokens. And so this is actually taken from a paper where they were building an entity recognition model. But essentially what they do is the word Picasso will have its own word embedding, and then after that they'll split Picasso into individual characters, embed each of those characters, and then what you're looking at here is essentially the same thing that I just described, but now at the character level in terms of the model. And you can produce a feature array that corresponds to the word, that corresponds to character information in the word Picasso. And you can then take this feature array and concatenate it to your word embedding. So now you're passing character level information into that machine learning model. And really what we've seen is this doesn't have huge improvements in our test metric, but what it does do is in production, when you have weird misspellings of words, it allows us to be a bit more robust to that behavior. Spacey has been another thing that's been very useful for us. So this allows you to read in sort of additional features based on your text. And these can be a combination of either rule-based or machine learning-based features. So you can see some of these features that correspond to this text are to do with whether there's a capital letter in the word or not, or to do with the shape of that word itself. So they would be rule-based, but then some of these other features are actually generated by machine learning models. So for example, the pos tags or the dependency parsing. And so these are all more features that you can try and throw at this model to improve your test metric. And really, one of the things we've been focusing on more recently is trying to move away from all of this feature generation and different modeling techniques and try and look at text on a character level. So this is a really attractive idea that we're not in production with yet, and I think it really depends on your model bias. But this is a paper by the Facebook research team where they took the input text and split it into individual characters, embed each of those characters, and then pass that through a deep sort of VGG-inspired convolutional neural network to predict the output class. And the thing that's really attractive about this is you can now pre-process in the same way for any language. So, for example, earlier when we tokenized English text, we were essentially tokenizing on white space. If you then had to do the same thing for Mandarin or Chinese, you would have to completely change the way that you pre-process that data. And actually it's much more difficult to have the meaning of a token there. And so there are Stanford trained NLP models called chunking models that essentially will take in Mandarin or Chinese and try and split that into meaningful tokens. And none of that has to be done with a model like this. Also, you're almost never going to see unseen characters in production because your vocabulary now consists of characters. So unless you've got really wacky emojis being sent to your bot that are not in your training set or that are not in your data, then this is quite robust to that. But the problem with these models is that they take a really long time to train and they take a lot of data to train. So one of the things that I've been looking into is things like transfer learning on large data sets and then using those weights in a model with a smaller data set to try and fine tune to our problem. So moving away from improving the model, the output of this model is some confidence score. And typically we'll take the confidence score of the highest confidence score in the associated class. And so what you're looking at here is a demo model where we're looking at a histogram of incorrect and correct predictions. And then you can see that there's a confidence threshold that's been set at 0.5 here. And so what this allows us to do is if we receive low confidence from our model, we can respond to the user by saying something along the lines of, I'm sorry, I don't understand what you're saying. And this allows us to tune to decrease the number of false positives that we'll see from that system. And this really ties into how we think about our models on the whole. So earlier I was saying an intent classifier can have well over 100 classes in it. And especially in the context of NLP, we really want to understand performance per class. Because we have some business trade-off going on here between precision and recall. So for those of you who aren't aware, precision is essentially for each class, of all the times the model predicts that class, what percentage are correct. And recall is, for all of the things that you annotated to a given class, what percentage did the model correctly predict? And so there are cases where we want really high precision from intent. So you can imagine if we have some class that is delete the user's account without asking for permission or something crazy like that, then we really want to minimize the number of false positives in that scenario. Whereas if we have an intent that's more along the lines of sign the user up for a really valuable product, it's really important that we don't miss a case where the user wanted to do that. And so in that case, we'd actually be more focused on recall and precision. And so at Fin, we do a lot of thinking about these confidence thresholds and how we can tune them actually per class to get the behavior that we want from our classifier. So this ties into, I think, one of the interesting problems that we have, certainly experienced at Fin, is that if we increase the model complexity in this classifier, typically we see our test metrics improve. With the caveat that the model's confidence scores sort of cease to make sense. And so you're looking here at a well-calibrated model on the left and a poorly calibrated model on the right. So when the model is well-calibrated, it's very accurate when it's very confident, and it's not at all accurate when it's not very confident. The problem that tends to happen when you have a very deep model, or at least that we have experienced, is that you don't see that relationship anymore. And that really prevents us from using that confidence threshold in a meaningful way to control for precision and recall. So that's one of the things I'd love to get someone's opinion on later, but that we have been sort of dealing with at Fin. And I want to end with what is most challenging about this problem. So we have these models with masses of classes, and those classes are defined by humans. And so there's always going to be some kind of annotation there, and there's never going to be a complete boundary that describes that class. And so this is some fantastic work that we had done by some students actually from the UBC Master of Data Science program. And what they did was took the output from the softmax layer of our classifier, and they used dimensionality reduction to reduce that to 2 dimensions, and then color the points by the class that they've been annotated to. And so what this allowed us to do was to go in and see which utterances the model thinks are or which sort of bodies of text the model thinks are very similar to each other. And then we can clean up boundaries where we've sort of become almost confused about what we're annotating to. So this is a real example with 2 intents, thank you and goodbye. And you can see that there's a, sort of on the most zoomed out, I should freeze this, but on the most zoomed out view, you see that there's a bridge forming between the 2 classes. And if you zoom in on that and really look at where they're most confused between each other, you can see that most of the utterances consist of users who've come to our system and they've said, thank you very much, goodbye, in one utterance. And so it's up to us to define consistent annotation rules so that we decide which class they belong to or whether they should be annotated at all. And so this tool allows us to go in and really clean up those boundaries and drive them back apart from each other. Yeah, so that's everything I've got to say about how we use MXNet at Fin, and be happy to take some questions. So go for it.
Well, actually, one question just about your last slide.
Sure.
Did you consider using multi-label classification as well?
We have not, no.
But that would be more solution to your problem here, right? Like, you really say goodbye and thank you at the same time.
Yeah, it's like they're both acceptable predictions. Yeah, okay.
Yeah, so you mentioned that you guys tried both like full word embeddings, word embeddings from FastTag, so subword information, character embedding, character-based embeddings. What did you guys end up with?
So what we've ended up with is a model that uses bucketing.
Can you repeat the question, please? Can you repeat the question, please?
So the question was, of all the things I showed, what have we actually then ended up with in production? And so of all the improvements to that model. So what we've ended up with is a model that uses bucketing, and we're using that convolutional model for text classification. The reason for that is that they train sort of a mixture of really nice training speed, but also being able to have a lot of model complexity in there. And then in terms of word embeddings, we've actually not ended up using those in our production model. Character level features, we saw roughly a 0.5% improvement in our test metric. And then, as I mentioned earlier, we're not using that CNN, deep CNN character level classifier.
So sorry, you mentioned that did you end up using word embeddings or not at all?
No, so we're actually training our embeddings from scratch.
Okay.
Yeah.
But those embeddings, are they like trained per word or some word per character?
So those embeddings are trained at the token level.
Oh.
So we break, token.
And how big is the kind of vocabulary that you guys decide to settle for?
Yeah. So we're around 100,000 distinct tokens in our training set.
Do you guys hash? Like, say, if you end up with a word that's out of vocabulary, do you do any kind of hashing trick? Or
So what's currently happening with out of vocabulary words is that they're assigned the embedding corresponding to the least frequent word in our training set.
Okay, so you have one token for out of vocabulary.
Yes.
Okay.
Yeah. Yes.
Why wouldn't you use any intent classifier that's coming straight out of Spacey? That's the first question. Or could you bootstrap off one of those? Question 2 is for the intent recognition, it has to fit into a bigger chatbot-y framework.
Yeah.
Are you using Rasa or Dialogflow or something like that?
Right. So I'll answer the second question first. So our chatbot framework is built in-house.
In-house.
So we're handling context intents entities in our own system. And then the first question was why we're not using spacey models, for example?
Yeah, wouldn't it make sense to bootstrap off Spacey models?
Yeah.
Like if you're thinking transfer learning, right? I mean, Spacey's learned models and weights on multiple
Yeah, I guess
text.
for us to use those weights in our model, we'd have to have precisely the same model architecture. We have experimented with using both Dialogflow for intent recognition and Spacey's classification models. And what we see is Spacey, we're roughly sitting around 5% better on our test metric. In terms of, I think we spend a lot longer optimizing our model versus that one, so you can read into that what you will. And then in comparison to Dialogflow, we're essentially the same performance as Dialogflow's intent classification. Yeah, sure.
So in terms of system development, there must have been a point where you didn't have, so when you're starting off from scratch, you don't have enough data.
Yep.
Right? And then you get enough domain-specific data as you get enough users. So if you were to build a system, would you build it first using existing Spacey-type models and then sort of switch to the fact that you have enough data that you build your own intent classifier? Is that the right way to think about it?
Well, I guess when you're starting with this problem, you have no data of any of your classes. So like if we have a class that's like check account balance, then a Spacey model is not going to have any meaningful weights for predicting that. We actually use Mechanical Turk to source training data to see these intents, and then we consistently annotate the production data and try and move over to that as we go. Yes?
In the context of Thin AI, what are you looking? Why are you working with the character level method? The one that you wanted to break down the word to the letters and feed it to the system, because I think it will create some unwanted consequences for your work in the context of AI.
So you're saying why are we not using the character level features or the full
the character
deep
level
character
features
model?
in the context of your work, it sounds will create some problems. It's not, at least to me, but I'm asking what is the main purpose behind that method for your own work?
So the idea with character level features is, for example, if you want to say, I want to log in, there will be a trained embedding for each of those tokens. But if you say something like, I want to log in, then we may see behavior where that token doesn't have a pre-trained embedding. And so what we're trying to do with the character level information is still be able to pass meaningful features into that model to hopefully get towards the predicting the correct class.
But don't you expect any unwanted consequences with this way of feature?
We've not seen any unwanted behavior with character level features in our test set.
maybe we take one more question.
Sure. Yeah.
So besides CNN, have you, for example, used any other LSTM thing?
Yeah. So I've experimented with a few recurrent models.
Because I think usually there's the standard of auth results, basically more into the other sometimes.
Yeah. So I have experimented with recurrent models, and actually models that are a combination of both recurrent and convolutional. We don't see any meaningful improvement in performance. We do see that they take longer to train. And in terms of what is state-of-the-art on the public text classification datasets, we're really seeing things like the fast text classifier or deep character models or CNN models like this. So yeah, we have experimented with those.
Thank you very much.
Thank